Have you ever wondered why water forms droplets? Why does ice melt into liquid water and then evaporate into steam? The answer lies in the fascinating world of intermolecular forces. These forces are like invisible bonds that hold molecules together in liquids and solids. They are weaker than the forces that hold atoms together within a molecule. Those are called intramolecular forces, but they are still incredibly important. Welcome, science fans, to venture into the world of intramolecular forces. Before we dive into the world of intermolecular forces, let's take a quick look at their stronger counterparts, intramolecular forces. These are the forces that hold atoms together, a molecule. Think of them as the superglue that keeps molecules from falling apart. For example, in a water molecule, H2O, the bonds between the oxygen atom and the two hydrogen atoms are intramolecular forces. These bonds are very strong and require a lot of energy to break. Now, let's talk about the gentler, more subtle forces that exist in molecules, intermolecular forces. These forces are responsible for many of the properties of matter, such as melting point, boiling point, and viscosity. Imagine a group of people standing close together. They are not holding hands or hugging, but they are still attracted to each other and tend to stay close. That's kind of like intermolecular forces. London dispersion forces. Even atoms have a little sway. Even the smallest, simplest atoms experience intermolecular forces. These forces are not just limited to complex molecules or large atoms. They are universal and can be observed in the most basic elements of the periodic table. These forces are called London dispersion forces, and they arise from temporary fluctuations in electron distribution within atoms. These fluctuations are random and can happen at any moment, causing a shift in the electron cloud. Think of a helium atom. Helium is one of the simplest atoms, consisting of just 2 protons, 2 neutrons, and 2 electrons. Despite its simplicity, it still experiences these fascinating forces. It has 2 electrons that are constantly moving around the nucleus. These electrons are in a state of perpetual motion, never staying in one place for too long. At any given moment, there's a chance that the electrons might be a little bit closer to one side of the atom than the other. This uneven distribution of electrons creates a momentary imbalance in the charge distribution within the atom. This creates a temporary dipole, or a separation of charge within the atom. A dipole is essentially a pair of equal and oppositely charged or magnetized poles separated by a distance. This temporary dipole can then induce a dipole in a neighboring helium atom, leading to a weak attraction between the two atoms. This interaction is subtle but significant, as it contributes to the overall behavior of gases and other substances at the atomic level. When many helium atoms are present, these London dispersion forces collectively influence the properties of the gas. They play a crucial role in determining the boiling and melting points of substances, as well as their solubility and other physical properties. Understanding these forces helps scientists predict and explain the behavior of different materials under various conditions. It also aids in the development of new materials and technologies. London dispersion forces are just one type of intermolecular force. Others include dipole-dipole interactions and hydrogen bonding, which we will cover later in the video. Each type of force has its own unique characteristics and effects on the behavior of molecules. So even though atoms are incredibly small and seemingly simple, they exhibit complex behaviors that are influenced by these subtle forces. The sway of atoms, driven by London dispersion forces, is a testament to the intricate and dynamic nature of the microscopic world. The study of these forces continues to be a vibrant field of research, with new discoveries and insights emerging regularly. As we delve deeper into the atomic and molecular realms, we uncover more about the fundamental forces that shape our universe. In conclusion, London dispersion forces remind us that even the tiniest particles have a role to play in the grand tapestry of nature. Their subtle interactions are a key part of the story of matter and its many forms. Dipole-dipole forces opposites attract. In this section, we will delve into the fascinating world of molecular interactions, specifically focusing on dipole-dipole forces. These forces play a crucial role in the behavior of polar molecules and are fundamental to understanding many chemical processes. In molecules with permanent dipoles or polar molecules, we encounter dipole-dipole forces. These forces are a type of intermolecular force that occurs between molecules that have regions of partial positive and partial negative charge. The presence of these charges is due to the difference in electronegativity between the atoms in the molecule. These forces arise from the attraction between the positive end of one polar molecule and the negative end of another. This attraction is similar to the way magnets work, where opposite poles attract each other. The strength of these forces depends on the magnitude of the dipole moments and the distance between the molecules. Take formaldehyde, CH2O, as an example. Formaldehyde is a simple yet illustrative example of a polar molecule. Its structure consists of a central carbon atom double bonded to an oxygen atom and single bonded to two hydrogen atoms. The oxygen atom is more electronegative than the carbon and hydrogen atoms, so it pulls electron density towards itself. Electronegativity is a measure of an atom's ability to attract and hold onto electrons. In formaldehyde, the oxygen atom has a higher electronegativity compared to carbon and hydrogen, resulting in an uneven distribution of electron density. This creates a permanent dipole in the molecule, with the oxygen atom being slightly negative and the carbon atom being slightly positive. The partial charges on the atoms create a dipole moment, which is a vector quantity that has both magnitude and direction. The dipole moment points from the positive to the negative end of the molecule. When two formaldehyde molecules come close together, the positive end of one molecule will be attracted to the negative end of the other molecule. This interaction is a classic example of dipole-dipole forces in action. These forces are responsible for many of the physical properties of substances, such as boiling and melting points, solubility, and viscosity. Understanding dipole-dipole forces helps us comprehend how molecules interact in different environments and conditions, providing insights into the behavior of various chemical systems. Hydrogen bonding, a special kind of attraction. Hydrogen bonding is a fascinating and crucial concept in chemistry that plays a significant role in the properties of many substances. It is a type of intermolecular force that is stronger than van der Waals forces, but weaker than covalent or ionic bonds. This unique interaction is essential for understanding the behavior of molecules in various states of matter. Hydrogen bonding is a special type of dipole-dipole force that occurs when a hydrogen atom is bonded to a highly electronegative atom, like oxygen, nitrogen, or fluorine. These electronegative atoms attract the shared electrons more strongly, creating a partial positive charge on the hydrogen atom and a partial negative charge on the electronegative atom. This results in a strong attraction between the hydrogen atom of one molecule and the electronegative atom of another molecule. Let's compare ethanol, CH3TH2OH, and dimethyl ether, CH3OTH3. You'll learn more about these structures in organic chemistry, but you can pay attention for the sake of this example. Both of these compounds have the same molecular formula, C2H6O, but their structures and properties are quite different. Ethanol has a hydroxyl group, OH, while dimethyl ether has an ether group, OCH3. This difference in functional groups leads to significant variations in their physical properties, such as boiling points and solubility in water. Both have the same molecular formula, but ethanol has a higher boiling point. The boiling point of a substance is the temperature at which its vapor pressure equals the external pressure, allowing it to transition from a liquid to a gas. Ethanol's boiling point is around 78 degrees Celsius, while dimethyl ether's boiling point is much lower, at approximately -24 degrees Celsius. This stark contrast can be attributed to the presence of hydrogen bonding in ethanol. Why? Because of hydrogen bonding. The hydrogen bonds in ethanol create a network of strong intermolecular forces that require more energy to break. This means that more heat is needed to convert ethanol from a liquid to a gas, resulting in a higher boiling point. In contrast, dimethyl ether lacks hydrogen bonding, so its intermolecular forces are weaker, and it requires less energy to boil. In ethanol, the hydrogen atom of the hydroxyl group, OH, can form a hydrogen bond with the oxygen atom of a neighboring ethanol molecule. This interaction is not just a simple attraction, it involves a significant overlap of electron clouds, creating a bond that is much stronger than typical dipole-dipole interactions. This hydrogen bonding network is responsible for many of ethanol's unique properties, including its relatively high boiling point and its ability to mix well with water. This strong interaction leads to a higher boiling point for ethanol. The presence of hydrogen bonds means that ethanol molecules are more tightly held together, making it more difficult for them to escape into the gas phase. This is why ethanol boils at a higher temperature compared to dimethyl ether, which lacks such strong intermolecular forces. Understanding hydrogen bonding is crucial for grasping the behavior of many biological and chemical systems, as it influences everything from the boiling points of liquids to the structures of complex biomolecules like DNA and proteins. Ion dipole forces. When ions and molecules mingle. When ionic compounds dissolve in polar solvents, we observe ion dipole forces. These forces arise from the attraction between an ion and the partial charge on the end of a polar molecule. Think of dissolving table salt, NaCl, in water. The sodium ions, Na+, are attracted to the slightly negative oxygen atoms of water molecules, while the chloride ions, Cl, are attracted to the slightly positive hydrogen atoms. These ion dipole forces are responsible for the ability of water to dissolve many ionic compounds. In conclusion, mastering intermolecular forces is crucial for understanding the behavior of molecules in different states of matter. By grasping these concepts, you can better predict and explain the properties of various substances. From the dance of molecules to the mingling of ions and polar molecules, each interaction paints a vivid picture of the microscopic world. Keep exploring and experimenting to deepen your knowledge in chemistry. Thank you for watching. Be sure to have a nice night, and good night!